So we're talking about isometries, and in principle, that's a pretty big category of things, right? We could, in principle, have a lot of different ways to transform the plane while preserving distances between pairwise points. And so far, we've seen two examples of what we claim are isometries. We still have to prove it. Right? Translations, which simply shift the location of a figure from one place to another, and rotations, which turn a figure about a fixed origin through a fixed angle. And by way of definitions, and there's a reason for this that we'll talk about in a little bit, translations, rotations, and everything which is built out of them form a subclass of isometries called the direct isometries. At least that's what our authors call them. Sometimes in linear algebra, these are also called special. If you see that word elsewhere in the realm of transformational geometry, sometimes they're called special linear transformations. But then there's one more type of isometry that is not part of that category. Those are going to be the ones that we talk about right now, reflections. So if we think about what translations and rotations do, let's suppose that I start with a figure that looks like, I don't know, let's take the Superman symbol, which I'm not going to do justice to here, but, you know, it looks something like that, whatever. It actually is a letter S, right? If I apply a translation to that, and I move it somewhere else on the page, it's still a letter S. Right? If I apply a rotation to it, you know, no matter how much I rotate it by, it's still the same letter S. I can still read it. But if I apply a reflection to it, suddenly it doesn't appear as a letter S anymore, right? It's going to be this funny backward S. I'm not well versed in the Superman universe, but isn't that the symbol for Bizarro Superman or something? The backwards S, right? So reflections do that thing that the direct isometries don't do. Is that what we say is that they reverse orientation. You might think of it as a right hand. After you apply a reflection to it, turns into a left hand, right? There's no way to rotate or to translate a right hand that's going to make it into a left hand, right? They're fundamentally opposite. If you take a chemistry class and look at molecular structures, there's some of them said to have chirality, handedness to them. And the two different molecules that are the same except that one of them is a mirror image of the other can actually have very different chemical properties, which is super interesting, I think. So being able to pass between those two worlds through the mirror, if you will, is something reflections can do, but direct isometries do not do. So that is what separates these two categories. And direct isometries play well with orientation. They preserve orientation. That's what makes them direct isometries. And so in a way, a reflection is like a flipping, in the same way that taking the opposite of a real number is like a flipping, right? Multiplying by -1 is like a flipping. That if I do it twice, I end up back with a positive result again. So if I do two reflections, if I compose one reflection with another reflection, there's a chance that that composition might be preserving orientation, right? So that's one of the sort of tantalizing questions when we start to put these isometries together, and we'll discover what the relationships among them look like. And one of the questions is, if I compose a reflection with another reflection, I expect that's not going to be a reflection anymore. I expect it's going to be some direct isometry. Well, which one? Right? So that's something we'll get a chance to look at as we get deeper into the material. But that's the distinction we want to make now between direct isometries, which preserve orientation, handedness, and the one class of direct isometry, of inverse isometries called reflections, which reverse orientation. So let's look at how reflections are defined to close things out for today.